Tonight, we're going to explore something that seems slow and steady, but is actually one of the most powerful forces shaping our planet, the Himalayas. You've probably seen pictures of these mountains or heard their name before. Scientists study them constantly when talking about earthquakes, climate, and the Earth's crust. But here's what most people don't realize. When you truly understand how these mountains are still rising, when you grasp the forces pushing the Earth's surface upward, it changes how you see the planet we live on. This is not just tall rocks stacked together. It's a process so immense and relentless that it shapes weather, rivers, and even human history. And by the end of this journey, you're going to understand exactly why the Himalayas are still growing, how scientists measure these movements, and why nothing else on Earth works quite the same way. Before we go any further, if you enjoy this kind of deep and careful exploration, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. The Himalayas are the tallest mountains on Earth. They did not appear overnight, nor were they always there. Their story begins tens of millions of years ago, long before humans walked the Earth. The land that is now India was once part of a large continent called Gondwana. This continent lay far to the south, close to the South Pole. Over millions of years, the Indian landmass slowly moved north. It was not an easy journey. The land drifted over the soft, moving layer of the earth beneath, called the mantle. This movement was slow, almost imperceptible, at just a few centimeters each year. But over time, it was enough to carry a massive continent thousands of kilometers north. As India moved, it approached the southern edge of another landmass called Eurasia. Eurasia was already a large continent, stretching across much of what we now know as Europe and Asia. The space between India and Eurasia was once filled with ocean, called the Tethys Sea. This sea was wide and deep, home to creatures of the ancient world, from fish to small reptiles. Over millions of years, the ocean floor itself moved. Rocks and sediments sank, and layers of mud and sand piled up over time. These layers would later become important for the formation of mountains. The collision between India and Eurasia began roughly 50 million years ago. When India first touched Eurasia, the ocean between them was squeezed. The Tethys Sea slowly disappeared as India pressed northward. Sediments that had accumulated in the ocean were pushed, folded, and lifted. These sediments formed the base of the mountains. Large layers of rock, which once lay at the bottom of the ocean, were carried upward. This process is called uplift. It is slow and powerful, a force that can shape continents. Rocks that were once smooth and flat now became jagged and high. At first, the uplift was uneven. Some areas rose faster than others. The land bent, folded, and cracked under the pressure. Rivers and streams flowing from the rising mountains cut through the rocks. Over millions of years, these rivers carved deep valleys and gorges. Sediment from the mountains washed down into the plains below. This sediment built fertile soils in places like northern India and Nepal. The movement of rivers was guided by the uplift, and the uplift was guided by the movement of the plates. It was a slow, endless dance, with each step shaping the land in ways that can still be measured today. The collision of India and Eurasia is not just a story of rocks. It is a story of forces deep within the Earth. The crust, the outer layer of our planet, is broken into large plates. These plates float on the soft mantle below. As India moved north, it did not slide easily. The plate pushed, collided, and crumpled. Some parts of the land buckled upward, forming the highest peaks. Other parts were forced downward, creating deep valleys and basins. This is why the Himalayas have such extreme variation in height, from plains to peaks soaring above 8,000 meters. Fossils from the region tell another part of the story. Fossilized shells of ancient sea creatures can be found high in the mountains, far above the reach of the sea today. They are found in layers of limestone and shale, proof that this land was once underwater. Over time, the collision lifted these rocks thousands of meters above sea level. They remind us that the tallest mountains on Earth were born from the same ocean that once stretched between continents. Each fossil is a small marker of history, preserved in stone, showing the journey from sea to sky. As the mountains rose, the climate changed. The rising peaks blocked winds and created rain shadows, changing rainfall patterns across the region. This, in turn, influenced erosion. Rocks at the surface were worn away by rain, wind, and ice. Yet the land continued to rise faster than it eroded, keeping the mountains high. The Himalayas are a balance between uplift and erosion. Even today, rivers carry massive amounts of sediment to the plains, and glaciers grind down rock into fine powder, yet the peaks continue to climb. The story that began 50 million years ago is still unfolding. Sediment layers, folded rocks, and the shapes of valleys all reveal the history of the Himalayas. Geologists can read these features like pages in a book. Each fold in the rock tells of the immense pressure applied by the colliding plates. Each fault line marks where the land cracked under stress. The region is complex, with layers stacked like pages, each layer representing a different time in the Earth's history. By studying these layers, scientists understand how mountains form, how continents move, and how forces within the Earth shape the world we see today. The origin of the Himalayas also shaped life. The land that once was under the ocean became a home for plants, animals, and eventually humans. Forests grew in the valleys, rivers became highways for life, and the high peaks formed barriers that guided the movement of species. The mountains created isolated environments where unique plants and animals evolved. Today, the Himalayas are home to rare and specialized species, all living in a landscape that is still rising, still moving, still alive in a geological sense. Even though the collision of India and Eurasia began millions of years ago, it is not finished. The land continues to push upward. The mountains are still growing. Measurements with modern tools, like satellites and GPS, show that some peaks rise a few millimeters each year. While small, this movement is a direct continuation of the processes that began so long ago. The Himalayas are not a static landscape. They are a living testament to the power of the Earth's crust, a record of forces that move slowly, but leave marks that last forever. The origins of the Himalayas teach us about time on a scale far beyond human life. The mountains remind us that continents drift, oceans vanish, and rocks rise from the sea to the sky. They are evidence of processes that work over millions of years, invisible in a single lifetime, but clear when viewed across geological time. Every peak, every valley, every river is shaped by the collision of two continents, the slow push of plates, and the relentless work of nature's forces. From the Tethys Sea to the highest peak, the Himalayas tell a story that is still being written today. Even the tallest peaks bear marks of the ancient ocean. Limestone cliffs, once part of the sea floor, sit above clouds. Fossil shells peek out from cracks in rocks. The evidence is undeniable. The mountains are born from the ocean, lifted by collision, shaped by time. As the land moves, as the plates continue their push, the Himalayas will keep growing, understanding their origin is not just about knowing the past. It is about understanding the present and the forces that will shape the future. The story of their birth is a story of Earth, itself slow, powerful, and ongoing. The first rise of the Himalayas set the stage for everything else in the region. Rivers, valleys, and climate were all influenced by this uplift. Human societies that came much later would settle along rivers fed by the mountains, benefit from fertile soils, and contend with earthquakes as the land continued to adjust. The mountains influence rainfall patterns across South Asia, guiding agriculture and life. Their origin is not just geological, it is ecological and human in its effects. Each layer of rock and sediment, each fold and fault, carries a memory of the forces that shape the world, a memory that can be read, studied, and understood. The Himalayas began as a story of movement, pressure, and time. They continue as a story of uplift, erosion, and life. From the deep oceans of the past to the highest peaks today, the mountains remind us that Earth is alive with slow, persistent motion. Even the smallest measurements reveal the immense energy locked within the crust. By studying the origins of the Himalayas, we glimpse the processes that shape all mountains, all continents, and all landscapes. This knowledge connects us to the planet in ways that are both humbling and inspiring. The story is ancient, but it is ongoing, and every inch of the mountains carries its history in stone. Beneath the Himalayas, the earth is not still. The land above our feet moves, though the motion is so slow that it is nearly invisible to the human eye. The surface of the planet, the crust, is broken into large pieces called tectonic plates. These plates float on a softer layer beneath them, called the mantle. The mantle is not solid like rock at the surface, but it is not liquid either. It can flow very slowly over millions of years. This slow flow carries the plates, guiding their direction, speed, and interactions. The movement is a kind of slow conveyor belt, shifting continents, creating oceans, and raising mountains. The Indian plate, carrying the land of India, is one of these massive plates. It moves north at a steady pace, only a few centimeters per year. But over millions of years, this movement covers thousands of kilometers. As the plate advances, it encounters resistance. The Eurasian plate, already large and heavy, blocks the northward push. The collision is not sudden, like an impact of cars. It is gradual, a steady pressing together. Rocks at the edges of the plates bend, fold, and break. The force is enormous, enough to lift mountains higher and higher with each passing million years. The collision generates immense pressure. Deep below, the crust is compressed and thickened. Some of the land is forced upward, forming peaks that reach far above the clouds. Other parts are forced sideways, creating folds and ridges. When rocks break, they form faults. Some faults release energy suddenly in earthquakes. Other faults move slowly, creeping along as the land adjusts. The constant push of India against Eurasia is what keeps the Himalayas alive, continuing to grow, reshape, and change. This movement is guided by forces deep in the earth. The mantle, though solid, flows like thick syrup over long periods. Hot material rises from deep within the earth, spreads beneath the plates, then sinks back down as it cools. This rising and sinking is called mantle convection. Convection moves the plate slowly, carrying India northward. It also provides some of the energy that drives mountain building. Without the flow in the mantle, the plates would not move, and the Himalayas would not exist. The process is invisible but powerful, a hidden engine beneath the land. As the Indian plate pushes north, the Eurasian plate responds in different ways. In some areas, the land is forced upward, creating high peaks. In others, the crust is forced sideways, folding into ridges and valleys. The movement is not uniform. Some sections rise faster, while others move more slowly. Satellite measurements show that different parts of the Himalayas climb at different rates, even today. This uneven movement gives the mountains their jagged shapes, deep gorges, and wide valleys. It is a story written slowly, over millions of years, with forces that humans can measure but not feel in daily life. The plates themselves are made of different materials. The Indian plate carries continental crust, which is thick and buoyant. The ocean floor, once between India and Eurasia, is thinner and heavier. As India pushed north, it first carried oceanic crust. This crust sank beneath Eurasia in a process called subduction. Subduction creates deep trenches in the ocean and melts some of the rock, forming magma that can rise and create volcanic activity. But when the continental crust of India arrived, it was too light to sink. Instead, it pushed against Eurasia, forcing both plates to thicken and rise. This is why the highest mountains in the world are here, where two continents collide directly. The force of this collision is immense. Imagine pressing two thick books together, but with the force multiplied thousands of times. The rocks at the edge crumple. Some fold upward, creating peaks. Others are pushed sideways, forming valleys and ridges. Layers of rock that were once horizontal now tilt and bend. Some rocks are broken into fragments. Others are melted by heat and pressure deep below. The land is alive with motion, constantly adjusting to the immense energy of the plates pressing together. Earthquakes are a visible sign of these forces. Along the boundaries where plates press together, stress builds. When the stress becomes too great, it releases suddenly. The ground shakes. Mountains shift slightly, rivers change course, and landslides occur. Each earthquake is a reminder that the Himalayas are not static. They are moving, growing, and responding to the slow but unstoppable force of tectonic collision. Even areas that seem calm are still rising, still under pressure, still part of this vast, ongoing process. The collision also produces deep folds in the crust called napes. These are massive sheets of rock that have been pushed long distances from their original position. Some napes are thousands of meters thick, moved by the pressure of India pressing north. They stack upon one another, forming layers that rise into the peaks we see today. The shapes of these rocks tell geologists the history of the collision. By studying folds, faults, and napes, scientists reconstruct the long struggle between plates, seeing how the mountains have grown and predicting how they may continue to rise. Mantle convection continues to supply energy. Hot rock from the interior rises toward the surface, spreading beneath the plates. Cooler material sinks. This movement not only carries India north, but also applies upward pressure to the crust. The heat and motion from deep below the surface interact with the weight and movement of the plates above, producing a dynamic system. Mountains are lifted, folded, and fractured by forces that humans cannot see but can measure with instruments. The Himalayas are a surface reflection of this deep, invisible engine. Over time, the constant push and pressure have thickened the crust beneath the Himalayas. Where a normal continental crust might be 30 kilometers thick, the crust beneath the Himalayas can reach 70 kilometers or more. This extra thickness supports the extreme height of the mountains. Deep in the crust, rocks behave like soft clay over millions of years. They flow slowly, allowing the mountains above to rise without collapsing entirely. This combination of crustal thickening, folding, and mantle support keeps the Himalayas high and growing. The process of collision is slow but unrelenting. Measurements show that the Indian plate continues to move north at about 5 centimeters per year. This is a small distance in human terms, barely the length of a fingernail in a year. Yet over 1 million years, it is enough to move the entire landmass hundreds of kilometers. This relentless movement means that the forces shaping the Himalayas are ongoing. The mountains we see today are the result of millions of years of collision, and they will continue to evolve as long as the plates move. The landscape itself reflects the forces at work. Rivers wind through steep valleys, cutting through folded rock. Sediment is carried from the peaks to the plains. Landslides and erosion continuously shape the slopes. All of this happens on top of the slow upward push from the collision. Every fold in the rock, every tilted layer, every fault line is evidence of the immense, invisible energy pressing the land upward. The Himalayas are a visible record of tectonic power written in stone and soil. The role of mantle convection is not just to move plates, it also shapes the nature of the collision. Where the mantle rises, it can push the crust upward. Where it sinks, it can pull the plates downward slightly. This interaction affects where rivers form, where valleys develop, and where peaks rise. Over millions of years, these subtle variations influence the overall shape of the mountain range. The Himalayas are not a simple wall of rock. They are a complex structure, shaped by the interplay of surface movement, deep forces, and ongoing collision. Even today, the Himalayas remind us that the Earth is alive. The collision between India and Eurasia continues. The peaks rise a few millimeters each year. The crust thickens, and faults slowly adjust. Satellite measurements capture the movement, confirming what rocks and folds have shown for millions of years. The mountains are living records of tectonic forces, rising gradually but persistently, shaped by pressures too great for humans to feel directly. They are a testament to the power of plate tectonics and the slow, unstoppable motion of the Earth's crust. The study of tectonics also explains why the Himalayas are not uniform. Some peaks rise faster, some valleys deepen more quickly, and earthquakes happen more frequently in certain regions. The northward push of India is uneven, and the response of Eurasia varies depending on the thickness, strength, and temperature of the crust. This unevenness creates the jagged skyline, steep cliffs, and deep gorges that characterize the mountains. No two parts of the range behave exactly the same, yet all are part of the same ongoing collision. The Himalayas stand as a monument to forces far greater than any human activity. The collision that began tens of millions of years ago continues. Mantle convection, crustal compression, folding and faulting all contribute to the growth and shaping of the range. Rivers cut through the mountains, glaciers carve valleys, and erosion wears the peaks down. Yet the collision continues, pushing the mountains higher. The Himalayas are a living laboratory for studying plate tectonics, illustrating the power, complexity, and persistence of Earth's internal forces. In understanding the Himalayan collision, scientists gain insight into how mountains form elsewhere. The same principles apply to other ranges, though the Himalayas are the highest and most active. The lessons learned here inform earthquake studies, climate predictions, and the understanding of continental evolution. Observing how India pushes north, how Eurasia responds, and how mantle convection drives movement allows us to see the slow, immense power shaping our planet, 1 centimeter at a time. The Himalayas are not frozen in place. Even today, the mountains rise slowly, a few millimeters each year, a motion almost invisible without careful measurement. Scientists track this growth using modern tools that were impossible a century ago. Satellites orbit the Earth, sending signals that can detect tiny changes in the height of peaks and the movement of land. GPS stations anchored into rock record shifts in position, sometimes smaller than the width of a human hair. Yet over years, these shifts reveal the steady growth of the range. These measurements confirm what rocks and fossils have shown. The mountains are alive, continuing to climb. The uplift is not the same everywhere. Different regions of the Himalayas move at different rates. In Nepal, near the central high peaks, some areas rise more quickly than in other parts of the range. Bhutan shows a slightly slower growth, while parts of northern India at the foothills experience different patterns of movement. Tibet, on the northern side of the range, also rises, but more evenly across the plateau. These variations result from the complex structure of the crust and the way the plates interact. Where the pressure of the Indian plate is greatest, the land pushes upward faster. Where the stress spreads out, the growth is slower. The mountain's uneven rise creates the jagged landscape we see today. Peaks and ridges climb higher while valleys remain deep. This unevenness is a reflection of the forces at work beneath the surface. The collision does not produce a uniform block of rising land. Some sections buckle, fold, and stack, while others stretch and crack. Faults develop where the pressure is concentrated. These faults sometimes slip suddenly, producing earthquakes, and sometimes move gradually, adding a few millimeters each year. The combination of slow uplift and sudden shifts shapes the entire range. Earthquakes are not separate from the growth of the mountains. They are part of the process. When stress builds along a fault, energy accumulates in the rocks. Eventually, it is released in a sudden movement. The land shifts, sometimes rising slightly, sometimes sinking. Each quake is a tiny step in the mountain's vertical motion. Some earthquakes lift large blocks of rock by several meters, while the slow creep along a fault contributes millimeters over years. Together, these movements maintain the Himalayas' height and continue the work begun tens of millions of years ago. Satellites reveal subtle changes in the land surface. By comparing images over years, scientists can see which areas rise faster, which move sideways, and which remain more stable. These observations are combined with GPS data on the ground, where stations measure the tilt, shift, and rise of rock in real time. Through careful study, patterns emerge. The central Himalayas often rise faster than the edges. Peaks like Everest and Kanchenjunga continue to grow, though erosion from glaciers and rivers removes rock at the surface. The interplay between uplift and erosion is delicate, yet the mountains maintain their towering heights. The rate of growth varies not just from region to region, but also from peak to peak. Some mountains gain a few millimeters per year, while others may rise more slowly. These differences depend on local geology, the thickness of the crust, and the arrangement of faults. Thick blocks of crust respond differently to pressure than thinner or fractured areas. Some blocks tilt as they rise, creating the steep slopes and sharp ridges typical of the Himalayas. Even small differences in uplift can change river patterns, influence glacier flow, and alter sediment transport over long periods. Valleys tell the story of ongoing growth as well. Rivers cut deeply into the rising mountains, carving gorges and carrying sediment to the plains below. The more quickly the peaks rise, the more energy rivers have to cut through rock. This creates a continuous feedback loop. Uplift raises the land, erosion wears it down, and the land responds by rising again. Satellite observations show that riverbeds shift over time, sometimes capturing evidence of sudden earthquake-induced changes. and other times marking the slow response of the mountains to steady uplift. In addition to vertical growth, the Himalayas also experience horizontal motion. Plates continue to push northward, causing the mountains to fold, compress, and stretch sideways. This horizontal motion contributes indirectly to uplift. As rocks fold and stack, peaks are carried higher. Folds visible in cliff faces and valley walls reveal the layers of rock that have been compressed and pushed upward over millions of years. Scientists can measure the angle and direction of these folds to understand how the land is still moving today. Glaciers interact with the ongoing uplift as well. Thick ice presses on the land beneath, slowly grinding rock, yet when the ice melts, pressure is released, and the land can rise slightly in response. This process, called isostatic rebound, adds a small but measurable amount to the mountain's growth. In some areas, the combined effects of plate collision, earthquakes, and glacial rebound create an upward motion that is greater than erosion can remove. In others, erosion matches or slightly exceeds uplift, showing that the balance between growth and wear is delicate and variable across the range. The northern and southern sides of the range do not rise at the same rate. The southern slopes, closer to the Indian plate, experience more compression and faster uplift. The northern Tibetan plateau rises more evenly but covers a larger area. This difference explains why rivers such as the Ganges and the Brahmaputra cut so deeply into the southern slopes, while the northern plateau remains relatively flat despite its high elevation. The variation in uplift shapes not only the height of peaks, but also the drainage patterns, ecosystems, and climate of the region. GPS measurements reveal movement even in small hidden areas. Rock that seems solid and unchanging can creep upward a few millimeters each year. These tiny shifts accumulate over decades, raising entire ridges and valleys. The data also show that earthquakes sometimes accelerate or temporarily reduce this motion. Large seismic events can instantaneously lift sections of the mountains, adding meters to certain peaks. Smaller tremors add only millimeters, yet over centuries they leave lasting marks in the land. Scientists also use satellites to track horizontal shifts. By measuring both vertical and horizontal motion, researchers understand how uplift is linked to the broader motion of the plates. In some cases, horizontal compression pushes rocks upward like a giant folding of paper. In other cases, the land slides slightly along a fault, while still rising slowly. The combination of vertical and horizontal forces explains why the Himalayas have such sharp ridges, steep cliffs, and deep valleys. The rate of uplift is not constant over time. Some peaks have periods of faster growth, followed by slower periods. These variations are caused by changes in plate movement, accumulation of stress along faults, and local geological conditions. By studying patterns over decades and centuries, scientists can identify areas at higher risk for earthquakes and landslides. They can also predict which peaks are likely to rise faster in the coming years, providing a dynamic picture of ongoing mountain growth. Erosion interacts with uplift in subtle ways. Rivers transport debris from high elevations to the plains, while landslides and glacial melting remove rock from steep slopes. The Himalayas maintain their height because the uplift often exceeds erosion, but the process is continuous. Every storm, every glacier movement, every river flow plays a role in shaping the peaks, while the crust continues to push them upward. In this way, the mountains are not just rising, they are being sculpted continuously. Earthquakes remain intertwined with uplift. Along active faults, blocks of land can rise suddenly during a quake. Some tremors lift rock by several meters, while slower fault movement adds millimeters each year. Each event alters the local pattern of growth, sometimes redirecting rivers or changing slope angles. Over millions of years, these small and large events combine, producing the dramatic relief and towering peaks of the Himalayas. Modern technology allows scientists to watch the mountains in real time. Satellites provide detailed images of movement, and GPS networks measure vertical and horizontal shifts. Together, these tools reveal the ongoing story of the Himalayas' growth. Peaks continue to rise, valleys deepen, and the land responds to the relentless push of the Indian plate. By combining geological evidence with direct measurements, researchers understand not only where the mountains are today, but how they are likely to continue growing in the future. Through this continuous monitoring, it is clear that the Himalayas are not static monuments. They are dynamic landscapes, rising slowly but persistently. Each millimeter of growth, each small shift along a fault, each upward movement recorded by GPS is part of a process that began tens of millions of years ago. The mountains are living records of tectonic energy, showing both the power and the subtlety of Earth's internal forces. The ongoing uplift shapes everything around the mountains. Rivers respond, glaciers adjust, valleys expand, and peaks grow higher. Even human settlements are affected, as small shifts can influence river courses, slope stability, and the risk of earthquakes. The Himalayas are a reminder that the planet is never still. The processes that began with the collision of India and Eurasia continue today, quietly lifting the land, folding the crust, and shaping a landscape that will remain high for millions of years to come. The Himalayas are not only mountains, they are also a record of constant shaking. The collision of India and Eurasia builds tension in the rocks beneath the surface. This tension is released in earthquakes, which happen when the stress along faults becomes too great. The faults are cracks or fractures in the Earth's crust where movement occurs. In some places, the rocks slowly bend and slide over time, but in other areas, the stress accumulates until it suddenly breaks, sending waves of energy through the land. These waves shake the ground, sometimes gently, sometimes violently, and are a reminder that the mountains are alive with movement. Earthquakes have shaped the Himalayas for millions of years. Geological evidence shows that major earthquakes have occurred repeatedly, creating terraces, landslides, and shifted river channels. Some quakes lifted blocks of rock by meters, forming scarps along the valleys. Ancient sediments buried by landslides reveal a history of repeated shaking. By studying these signs, scientists can trace patterns of activity, identifying zones where energy accumulates and where it is released. This record is written in stone, a story of tension, strain, and sudden motion. The largest earthquakes in the region can reach magnitudes above 8 on the Richter scale. Historical records, combined with modern seismic instruments, show that quakes of this strength can destroy towns, redirect rivers, and change the course of valleys. Some of the most destructive events occurred in areas of Nepal and northern India. These quakes remind us that the forces building the mountains are not quiet. The uplift, the folds, and the pressure that create high peaks also store enormous energy that can be released in moments. Fault lines are the highways along which this energy travels. Some faults are long and straight, extending for hundreds of kilometers. Others are short, curving, or broken into smaller sections. The main faults in the Himalayas lie along the boundary, where the Indian plate presses into Eurasia. These faults carry most of the movement from the collision. As the plates continue to push against each other, stress builds along these fractures. The rocks bend and compress, sometimes creeping slowly, sometimes locking, until a large quake occurs. Earthquake dynamics are linked closely to uplift. When a fault slips, it can raise or lower parts of the land. In some cases, peaks rise by meters in a single event. This sudden movement is a small but powerful addition to the ongoing growth caused by plate collision. Over thousands of years, repeated earthquakes lift the mountains, move valleys, and alter the flow of rivers. The Himalayas' extreme relief is partly the result of these repeated seismic events, layered over millions of years of gradual uplift. The process begins with strain accumulation. As India pushes north, the rocks along the plate boundary deform. Some areas absorb the movement by bending, while others lock in place. Locked faults store energy. The longer the fault remains locked, the greater the strain. Eventually, the stress exceeds the strength of the rocks. The rocks snap, releasing the energy in waves that travel outward. This sudden release is what humans feel as an earthquake. While brief in duration, the shaking is a direct consequence of forces that act over millions of years. Smaller earthquakes also occur frequently. These microquakes often go unnoticed by people, but are recorded by seismometers. They relieve some stress along faults, shifting the land by millimeters or centimeters. Over time, they contribute to the movement of mountains. The combination of large, destructive quakes and small, frequent tremors creates a pattern of motion in which the Himalayas grow and adjust continuously. The land rises, shifts, and bends in response to the ongoing push of the plates. Major earthquakes leave visible marks in the landscape. River terraces can be raised or tilted, cliffs can crack, and entire hillsides can move. Landslides triggered by quakes reshape valleys and redirect water. Some rivers suddenly deepen their channels after a quake, and sediment is carried downstream in large amounts. The effects of a single event may last for centuries, changing the landscape permanently. Over time, repeated earthquakes shape the topography as effectively as the slow uplift from plate collision. Communities have long felt the power of these tremors. Towns in the Himalayan foothills are vulnerable because they are built on unstable slopes or river terraces. Earthquakes can destroy homes, block roads, and disrupt rivers. Historical records show that settlements have been wiped out multiple times by quakes, only to be rebuilt later. Even today, seismologists monitor these regions closely, using knowledge of faults and strain accumulation to predict areas of higher risk. The mountains, while majestic, carry both natural beauty and hidden danger. The timing of earthquakes is unpredictable. Large events may occur decades or centuries apart, while smaller tremors happen regularly. This unpredictability is a result of the slow, irregular accumulation of stress. Some faults may remain locked for hundreds of years, while neighboring faults move more freely. By combining historical records, geological surveys, and modern instruments, scientists can map active zones, revealing which regions are more prone to sudden uplift or shaking. These maps guide disaster preparation and help understand the ongoing growth of the mountains. Earthquakes are part of the balance between stress and release in the Himalayas. The collision of India and Eurasia forces the crust to rise, bend, and fold. Faults store energy, then release it. Some movement is gradual, some is sudden. Together, these processes contribute to the growth and shaping of the mountain range. Peaks that seem permanent are, in fact, responding to forces below, rising with each tremor and adjusting with each landslide. The landscape is alive, slowly but powerfully, with every earthquake marking a moment in its long story. Geological studies show that areas near major faults experience more frequent vertical motion. In these zones, uplift from plate collision and earthquake movement combine. Some regions gain several meters of elevation over thousands of years. These changes are recorded in river terraces, cliff faces, and sediment layers. By observing these features, scientists reconstruct a history of repeated earthquakes and uplift. The mountains are, in this way, both the record and result of seismic activity. The relationship between earthquakes and rivers is especially clear. When a quake lifts a block of land, rivers may suddenly steepen, accelerating erosion. Landslides can block river flow temporarily, forming natural dams. Water pressure builds, and eventually rivers break through, carrying enormous sediment downstream. This interaction between earthquakes, uplift, and rivers is a key part of how the Himalayas maintain their shape, with peaks rising even as valleys deepen. Glaciers are also affected by earthquakes. Tremors can fracture ice, trigger avalanches, or change the slope of the land beneath. When ice moves suddenly, it adds to erosion and sediment transport. These processes, combined with vertical growth from plate collision, create a dynamic landscape where mountains, rivers, and ice constantly adjust. The Himalayas are a complex system in which tectonic energy, seismic activity, and natural erosion work together. Monitoring earthquakes today combines multiple methods. Seismometers measure vibrations, GPS stations track subtle land shifts, and satellites detect changes in topography. These tools allow scientists to see both the slow buildup of strain and the sudden release during quakes. By studying the patterns, they understand which areas are rising fastest and which are most likely to experience future events. The Himalayas continue to grow, not smoothly, but in fits and starts, with earthquakes playing a central role. Historical earthquakes, such as those in Nepal in 1934 and in India in 1950, illustrate the power of the region. Large sections of land shifted, rivers changed, and entire towns were destroyed. Rocks were lifted, landslides occurred, and sediment was carried to the plains. These events show how plate strain, once accumulated, can release in a single day what took decades or centuries to build. They are a reminder that the growth of the Himalayas is not only slow and steady, but also punctuated by sudden, powerful changes. Seismic activity is also connected to the highest peaks. Areas around Mount Everest and Kanchenjunga lie near active faults. Measurements show that earthquakes contribute to local uplift, adding to the ongoing growth from plate collision. The peaks continue to rise in small increments, and the record of past quakes is preserved in folded rock, scarps, and displaced sediments. Each earthquake leaves a subtle but permanent mark, a contribution to the mountain's ongoing formation. The study of earthquake dynamics explains much about the Himalayas' present and future. By understanding fault lines, strain accumulation, and release, scientists can see how the mountains respond to internal forces. Vertical growth, horizontal compression, and seismic release all combine to shape the peaks and valleys. The Himalayas are not static. They are constantly adjusting, slowly rising, bending, and cracking in response to the relentless push of the Indian plate and the resistance of Eurasia. Earthquakes are not random disturbances, but integral to the mountain's evolution. They redistribute stress, raise peaks, carve valleys, and influence the flow of water and ice. Over millions of years, the repeated shaking contributes as much to the landscape as the slow, steady collision of plates. By observing both past events and current movements, scientists can trace the relationship between seismic activity and uplift, seeing how the forces beneath the Earth shape the world above. The Himalayas' height, jagged ridges, and deep gorges are, in part, a record of seismic events. Large quakes lift blocks of rock, small tremors adjust the land subtly, and rivers and glaciers respond. Communities have adapted to living in this dynamic environment, building on terraces and avoiding slopes most prone to sudden motion. Yet the mountains themselves continue to grow, rise, and change, driven by forces that humans can measure but cannot stop. Through the study of earthquakes, we see the Himalayas as living structures. The land is slowly rising, bending and breaking, while faults release energy in unpredictable but measurable ways. The peaks, valleys and rivers all reflect this process. Seismic activity, far from being a separate phenomenon, is a direct and ongoing expression of the forces that build and shape the tallest mountains on Earth. Every tremor, every fault slip, every sudden rise is part of the same story. The Himalayas are still growing. The Himalayas are covered with ice in many regions. Glaciers, thick rivers of ice, move slowly down the slopes. They carve the rock beneath them, shaping valleys and ridges as they flow. Glaciers do not move quickly. They inch forward over years, sometimes only a few meters in a year, yet their impact is profound. The ice grinds against rock, scraping surfaces smooth in some places and leaving deep grooves in others. This carving action creates U-shaped valleys, broad at the base and steep along the sides, a shape different from the narrow V-shaped valleys formed by rivers alone. As glaciers move, they pick up rock, sand and soil, carrying this debris far from its source. This material, called moraine, is deposited at the edges of glaciers and in the valleys below. Moraines form ridges of rock and sediment that mark the furthest reach of ice during past glacial periods. Some moraines are still visible today, hundreds or thousands of years after the glaciers retreated. By studying these deposits, scientists can understand the size, movement, and speed of ancient glaciers and how they help shape the landscape. The rivers of the Himalayas are fed by melting glaciers. During warmer months, the ice melts and flows downhill, carrying sediment picked up along the way. Rivers cut through rock, transport material to lower plains, and deposit silt in floodplains and deltas. The sediment shapes the land over time, building fertile soil far from the mountains. This process is a natural extension of glacial activity. Ice and water together carve the mountains, moving vast amounts of rock and shaping valleys that support life for humans and animals alike. Glacial erosion and uplift interact continuously. As tectonic forces push the mountains upward, glaciers respond to the higher elevations and colder temperatures. The ice increases in thickness and energy, carving valleys more deeply. At the same time, erosion removes material from the peaks and ridges. This removal lightens the load on the crust, allowing some sections to rise slightly faster in a process called isostatic adjustment. The mountains are shaped by both the slow push from below and the grinding of ice from above, a dialogue between growth and wear that has continued for millions of years. Rock formations tell the story of this interaction. Cirques, bowl-shaped depressions at the heads of glaciers, mark where ice accumulated. Hanging valleys, perched above the main valley floor, show where smaller glaciers joined larger ones. Striations and polished rock surfaces record the movement of ice over stone. Every feature is a testament to the combination of uplift and erosion, revealing how glaciers reshape the mountains, even as the land rises beneath them. Erosion also affects the steepness and stability of the slopes. Ice and rivers wear down cliffs, making some areas prone to landslides. Avalanches and rockfalls occur as erosion weakens rock faces. Glacial valleys often contain lakes formed where ice once blocked water, or where moraine created a dam. These lakes continue to influence river systems, storing and releasing water seasonally and shaping sediment transport downstream. The landscape is dynamic, constantly adjusted by ice, water, and rock. The scale of glacial erosion is immense. Large glaciers can move hundreds of meters of rock over thousands of years. Combined with sediment carried by rivers, these forces shape the foothills, valleys, and plains around the mountains. Erosion can counteract some of the uplift, keeping the mountains from rising infinitely high. Yet, the rate of uplift often exceeds erosion, allowing peaks to remain extremely tall. The Himalayas are a balance between these two forces, rising slowly while being carved simultaneously by ice and water. Glacial deposits are not uniform. Some valleys are filled with coarse boulders, while others carry fine silt or sand. The size and distribution of this material influence river flow, soil formation, and vegetation. As glaciers advance and retreat, they create a patchwork of landforms, leaving behind a record of past climate conditions. By analyzing these sediments, scientists can reconstruct the history of ice movement, rainfall patterns, and the timing of tectonic uplift. Rivers themselves continue the work started by glaciers. Meltwater carves channels, transports sediment, and shapes floodplains. The Ganges, Indus, Brahmaputra, and their tributaries originate in the Himalayas, carrying glacial melt and eroded rock to the plains below. Seasonal variation in flow sculpts valleys and reshapes slopes, constantly moving material from high peaks to lower regions. This sediment nourishes soils, supports agriculture, and maintains the ecological balance of regions far from the mountains. Valleys carved by glaciers are often steep and narrow at higher elevations, widening as rivers carry debris downward. Terraces form where sediment is deposited along riverbanks. These terraces reveal the history of erosion and uplift over millennia. In some areas, earthquake activity raises terraces suddenly, while rivers adjust gradually to the new height. The interplay of tectonic uplift, seismic activity, glacial carving, and river erosion produces the complex, rugged terrain typical of the Himalayas. Glacial retreat exposes freshly carved rock. As glaciers shrink during warmer periods, they leave behind steep cliffs, moraine ridges, and rock debris. This exposed land becomes subject to further erosion by rain, wind, and rivers. Weathering breaks down rock, and streams transport the fragments downstream. Over thousands of years, these processes smooth rough surfaces, fill valleys with sediment, and contribute to long-term landscape evolution. The mountain surfaces are continuously modified, even as they rise. Ice also forms natural dams and channels for rivers. Meltwater may pool behind moraines or glacial ridges, creating lakes. When these dams fail, sudden floods occur, transporting enormous amounts of sediment rapidly. These glacial lake outburst floods carve new valleys and reshape the river landscape. They are dramatic examples of how ice interacts with water and rock to influence the ongoing development of the mountains. Erosion helps expose the deep structure of the mountains. As glaciers and rivers remove material from the surface, folded and faulted rocks become visible. Geologists can study these exposed layers to understand how tectonic forces shape the range. The combination of uplift, glacial carving, and river erosion allows scientists to see both the surface effects and the deeper processes responsible for the Himalayas' formation and growth. Long-term landscape evolution is a story of balance. Uplift raises peaks, glaciers carve valleys, rivers transport sediment, and erosion removes excess material. Over millions of years, this balance produces the high peaks, steep ridges, and deep valleys that define the Himalayas today. No single force dominates. Instead, the mountains are shaped by the interaction of ice, water, rock, and tectonic energy, each influencing the other, in a continuous cycle. Vegetation responds to these changes as well. Forests grow on stable slopes, while bare rock and moraine dominate areas with active glacial or river erosion. Sediment deposited by rivers creates fertile valleys that support life. The landscape is not only geological but ecological, shaped by the movement of ice and water, and influenced by the slow rise of the mountains themselves. The scale of glacial shaping is immense when viewed over geological time. Valleys can be carved hundreds of meters deep. Rivers can transport millions of tons of sediment, and peaks continue to rise slowly despite the wear from erosion. Glaciers leave behind a permanent record of their movement. Striated rocks, polished surfaces, and moraines that mark their former extent. These features are clues that scientists use to understand the history of uplift, climate, and erosion in the region. Even small glaciers contribute to erosion. Ice in narrow valleys or hanging glaciers presses against rock, carving niches and small depressions. Over thousands of years, the combined effect of many small glaciers can be as significant as the largest ice flows. The cumulative work of ice, rivers, and weathering gradually sculpts the mountains, shaping the rugged terrain that is characteristic of the Himalayas. The Himalayas' sharp peaks and deep valleys are the result of continuous interaction between tectonic uplift and erosion. Ice and water carve away the rocks as the land rises. Rivers carry debris to distant plains, and glaciers leave behind moraines and polished rock surfaces. Over millions of years, these processes produce the dramatic landscapes we see today. The mountains are not static monuments. They are active, shaped by forces above and below the surface, a record of movement, pressure, and time. Through this ongoing cycle, the Himalayas maintain their height, while slowly evolving in form. Peaks rise, valleys deepen, and rivers continue to transport sediment. Glaciers carve and reshape the land, leaving behind clues about past climates and ice movements. The interaction between uplift and erosion ensures that the mountains remain dynamic, constantly changing, yet always monumental. The story of glacial shaping and erosion is inseparable from the story of the Himalayas themselves, a continuous shaping of Earth's tallest mountains by ice, water, and rock. The climate of the Himalayas plays a powerful role in shaping the mountains. Rain and snow fall unevenly across the range, creating a mosaic of wet and dry areas. Monsoon winds sweep from the south, carrying moist air from the Indian Ocean. As these winds rise over the mountains, the air cools and releases water. The southern slopes receive enormous amounts of rainfall, while the northern slopes, in the rain shadow, remain much drier. This difference in precipitation influences rivers, glaciers, and erosion rates, and in turn affects how the mountains evolve over time. Heavy rainfall contributes directly to erosion. Water running down slopes wears away rock and soil, deepens valleys, and shapes ridges. Streams merge to form rivers, which carry sediment from the high mountains to the plains below. During monsoon seasons, rivers swell, moving enormous quantities of debris. Landslides become more frequent as saturated soils lose strength and cliffs collapse. These processes wear the mountains down even as tectonic forces push them up, creating a balance between growth and erosion that shapes the landscape continuously. Snow and ice also influence mountain growth. Snow accumulates at high elevations, feeding glaciers that slowly move downhill. When snow melts, it produces runoff that contributes to rivers and sediment transport. Seasonal cycles of accumulation and melting create fluctuations in river volume and erosion intensity. In some regions, heavy snowfall and glacial ice can press down on the crust. When the ice melts, the land rebounds, rising slightly. This interplay between ice and rock links climate directly to the physical growth and adjustment of the mountains. Climate patterns vary over time. Monsoons may strengthen or weaken, and snowfall may increase or decrease depending on broader climate cycles. These changes influence the rate of erosion, the stability of slopes, and the flow of rivers. Stronger monsoons intensify rainfall, causing more landslides and higher sediment transport. Weaker monsoons reduce erosion, but also reduce water flow to glaciers and rivers, slowing some of the landscape's movement. The Himalayas respond dynamically to these shifts, their form shaped by both weather and tectonics. Erosion and climate create feedback loops with tectonic activity. As the mountains rise, air is forced upward, cooling and releasing precipitation. This rainfall accelerates erosion, removing rock from peaks and slopes. As material is carried away, the crust lightens slightly, allowing the mountains to rise faster in some areas. This process connects rainfall, erosion, and tectonic uplift in a continuous cycle. The highest peaks are often located where precipitation is greatest, demonstrating the intertwined nature of climate and growth. Glaciers respond to both precipitation and temperature. During colder periods, glaciers advance, carving valleys and transporting rock. In warmer periods, glaciers retreat, exposing steep cliffs and depositing moraine. These shifts not only shape the landscape, but also influence how the crust responds to weight and pressure. The ice adds mass that depresses the crust, and when it melts, the land rebounds. Over thousands of years, these cycles of ice growth and retreat have contributed to the complex topography of the Himalayas. Rainfall patterns also control sediment transport. Streams fed by monsoon rains carry rock and soil from high elevations to lower plains. The material builds river terraces, floodplains and deltas far from the mountains. In areas with extreme rainfall, landslides can move large boulders and reshape valleys quickly. In drier regions, erosion is slower, and valleys remain steeper and narrower. This variability affects the balance between uplift and erosion, influencing where peaks rise fastest and where valleys deepen over time. The impact of climate on tectonics is subtle but real. Heavy rainfall and snowmelt lubricate faults and fractures, making them more likely to slip. Saturated soil and weakened rock can trigger landslides and small earthquakes. Over long periods, these processes interact with the northward push of India, the thickening of the crust, and the formation of folds and ridges. Climate is not the primary force raising the Himalayas, but it shapes how the mountains adjust to tectonic stress and how quickly erosion removes material. Temperature changes also affect erosion rates. Cold temperatures slow chemical weathering, but enhance frost cracking. Where water freezes in, rock crevices and expands, breaking the rock apart. Warm temperatures accelerate water flow, increasing river erosion. Seasonal and long-term climate fluctuations influence the balance between these processes, determining how fast slopes erode and valleys deepen. Over millions of years, this interaction has helped sculpt the jagged peaks, cliffs, and ridges of the range. Vegetation responds to climate as well. Forests on wetter slopes stabilize soil, slowing erosion. Where rainfall is sparse, soil is thinner, and slopes are more prone to landslides. The distribution of plants, snow, and ice creates microclimates that influence the shape and stability of the mountains. For example, shaded valleys may retain ice longer, while exposed slopes may experience faster rock weathering. The interaction of climate, life, and geology produces a complex system where each factor influences the others. Modern climate change is altering these dynamics. Rising temperatures accelerate glacial melting, increasing river flow and sediment transport in some areas, while reducing ice mass elsewhere. Changes in monsoon patterns can lead to more extreme rainfall events, increasing the frequency of landslides and floods. These shifts affect both erosion and the feedback with tectonic uplift, altering how the mountains evolve. Scientists monitor these changes closely, noting that the Himalayas remain dynamic, even as human activity influences climate and weather patterns. Seasonal variation is also important. During monsoon months, rivers swell, landslides occur more often, and erosion intensifies. During dry months, streams slow, glaciers advance more slowly, and sediment transport decreases. This rhythm of wet and dry seasons contributes to the shaping of valleys, terraces, and ridges. Peaks are carved gradually, and the interplay between rainfall, snow, and ice adds complexity to the mountain's ongoing growth. The feedback between erosion and uplift links climate directly to height. Where erosion removes large amounts of rock, the crust can rise more quickly. High precipitation and glacial activity increase erosion, accelerating this effect. Conversely, in drier regions or where erosion is slower, uplift continues, but peaks may not reach the same dramatic heights. Climate, therefore, is a subtle but essential sculptor, guiding how and where the Himalayas rise. Rivers act as conveyors, moving sediment created by rainfall and glacial melt to lower elevations. Floodplains accumulate layers of soil and rock, creating a long-term record of erosion and deposition. Landslides and glacial floods add sudden pulses of sediment, altering river courses and valley shapes. The balance between gradual erosion, sudden events, and tectonic uplift creates a constantly evolving landscape, shaped by the interaction of climate, water, and rock. Climate also affects human settlements and infrastructure. Communities in the foothills experience flooding, landslides, and changing river courses. Mountain roads, bridges, and towns are exposed to erosion and sediment movement. Monitoring precipitation, snowmelt, and river flow provides insight into both natural processes and how the mountain's growth interacts with life. These human observations complement scientific measurements, helping to understand the influence of climate on the Himalayan system. Over thousands of years, climate patterns have shifted repeatedly. Ice ages brought colder temperatures, expanded glaciers, and intensified erosion at high altitudes. Warmer periods caused glacial retreat, exposing rock to weathering. These cycles influence both the shape and height of the mountains. Peaks rose, valleys deepened, and sediment was transported to plains. Each climatic cycle added to the complex topography and ongoing growth of the range. The Himalayas are therefore a product of both tectonic forces and climate. The northward push of India drives uplift, but rainfall, snow, glaciers, and temperature variations shape the form of the mountains and affect how quickly material is removed. Climate is intertwined with erosion, tectonics, and sediment transport, creating a dynamic system where the mountains rise, while simultaneously being sculpted. Even small shifts in precipitation or temperature have long-term effects. A single intense monsoon can trigger landslides that reshape valleys. A series of dry years can reduce glacial flow and slow river erosion. Over centuries, these variations accumulate, influencing the mountain's evolution. Climate acts as both a sculptor and a regulator, working alongside tectonic forces to shape the Himalayas continuously. In this way, The Himalayas are a living record of climate interactions. Their height, steep slopes, and carved valleys reflect the combined influence of rainfall, snow, ice, and tectonic pressure. Glacial carving, sediment transport, and erosion respond to precipitation patterns and temperature changes, while uplift continues beneath the surface. The mountains grow, erode, and adjust in response to the rhythm of climate, showing the inseparable link between weather and geology. Through this ongoing process, the Himalayas demonstrate that climate is an active participant in mountain growth. Seasonal and long-term variations influence erosion rates, river patterns, and glacial movement. These effects feed back into tectonic processes, affecting how peaks rise and valleys deepen. The interplay of climate, erosion, and uplift ensures that the Himalayas remain a dynamic and evolving range, shaped by both the forces of the earth below and the patterns of weather above. The Himalayas are not only mountains of rock, ice, and snow. They are also home to an incredible variety of life. The range stretches across vast distances, from low foothills to the highest peaks, creating a series of ecological zones. Each zone has a unique climate, soil type, and plant cover. As the elevation increases, temperature drops and oxygen levels fall, making conditions harsher. These changes create distinct habitats, from warm, humid subtropical forests at lower elevations to cold, sparse alpine tundra at the highest peaks. The subtropical forests of the foothills are dense and green. Trees such as sal, oak, and pine dominate the landscape. Rainfall is abundant, and the soil is rich in nutrients carried down from higher elevations by rivers and landslides. These forests support a wide array of wildlife. Monkeys swing through the trees, deer graze in clearings, and birds of many colors fill the canopy with song. Insects and small mammals thrive in the thick undergrowth, feeding on leaves, seeds, and fruits. The forests are alive with movement and sound, a direct product of the stable soils and plentiful rainfall of the lower mountains. As the land rises, subtropical forests give way to temperate forests. These middle elevation zones are cooler and often steeper. Trees such as rhododendron, fir, and maple dominate. The ground is carpeted with moss, ferns, and smaller shrubs. Wildlife adapts to these changes. Species that need cooler temperatures or more rugged terrain find suitable habitats here. Leopards, red pandas, and Himalayan tahr move through these zones, finding food, shelter, and breeding grounds. The diversity reflects both the climate and the geological complexity of the mountains, where steep valleys and ridges create isolated pockets for life to thrive. Above temperate forests, subalpine and alpine zones begin. Trees become smaller and more scattered. Shrubs, grasses, and hardy flowering plants dominate. These areas are cold for much of the year, with snow covering the ground in winter. Only species adapted to low temperatures survive here. Snow leopards, blue sheep, and pika are examples of animals that have evolved to cope with limited oxygen, scarce vegetation, and harsh winters. Their presence is directly connected to the altitude and terrain created by tectonic uplift and glacial erosion. The highest peaks and ridges reach the alpine tundra. Here, the land is mostly rock, ice, and sparse vegetation. Mosses and lichens cling to rock faces, while small flowering plants bloom in short summer periods. Wildlife is minimal but highly specialized. Only a few insects and birds, such as snowfinches, survive. Mammals at these heights must endure extreme cold, wind, and low oxygen levels. These species have evolved unique adaptations, such as dense fur, slow metabolisms, and specialized lungs, allowing them to live in conditions that would be impossible for most animals. Elevation and geological processes shape species distribution. As the land rises through tectonic uplift, it creates new slopes, ridges, and valleys. Rivers cut deep into the rock, forming gorges and isolated pockets. Glaciers carve high-altitude lakes and cirques. These geological features isolate populations of plants and animals, leading to distinct ecological communities. A species on one ridge may be entirely different from a species on a neighboring slope, just a few kilometers away. The mountain's continuous growth and erosion create an ever-changing patchwork of habitats. The Himalayas are rich in endemic species, meaning species found nowhere else on Earth. Many plants and animals evolved in isolation, adapting to the specific conditions of a single valley, slope, or mountain range. Rhododendrons, orchids, and medicinal herbs have unique varieties restricted to particular elevations. The snow leopard and red panda are examples of mammals that evolved in response to the Himalayas' combination of elevation, temperature, and prey availability. Endemic species illustrate how uplift and geological change directly influence the course of evolution. Uplift itself creates ecological niches. As new peaks rise, new habitats appear at different altitudes. This vertical expansion allows life to colonize areas that were once too low or too warm. Over time, populations adapt to the conditions of these newly formed zones, developing physical and behavioral traits suited to their environment. For example, plants at higher elevations may have thicker leaves, deeper roots, or the ability to survive long periods of snow cover. Animals develop traits to cope with thinner air, colder temperatures, and rugged terrain. Glacial activity also contributes to habitat formation. Retreating glaciers leave behind moraines, rock debris, and temporary lakes. These features create microhabitats for plants and small animals. Sediment-rich soils in moraine valleys support hardy vegetation, while rock crevices provide shelter for birds, small mammals, and insects. Over centuries, these newly available habitats are colonized, contributing to the mosaic of biodiversity that characterizes the Himalayas. Rivers formed by glacial meltwater further influence ecological zones. River valleys create corridors for species to move between altitudes. Fish and amphibians live in streams, while birds and mammals use valleys for migration and feeding. The interaction between water availability, terrain, and temperature determines which species can survive in each part of the range. High flows during monsoon seasons reshape riverbeds, creating dynamic habitats for life that constantly adjust to the landscape's changes. The Himalayas' biodiversity is also a product of isolation. Steep cliffs, deep valleys, and glaciers prevent many species from mixing. Over long periods, populations become genetically distinct, leading to speciation. A plant species in one valley may evolve differently from the same type on another slope. Animals may develop unique adaptations depending on food availability, predation pressures, and microclimate. This isolation, combined with continuous uplift, drives the creation of new species and adds to the range's ecological richness. Elevation gradients also dictate climate, within the mountains shaping habitats. Lower zones are warmer and wetter, supporting dense forests. Mid-elevations are cooler, with seasonal snow and more rugged terrain. High zones are cold and dry, with ice and rock dominating. Plants and animals follow these gradients, creating vertical bands of ecosystems. Each band represents a unique combination of temperature, precipitation, soil, and slope. Uplift continues to change these gradients, gradually shifting habitats upward over millennia. Human influence is also present. though relatively limited at higher elevations. Communities in the foothills and lower valleys cultivate crops, graze livestock, and harvest forest products. These activities modify habitats, but they also interact with natural processes of erosion, river flow, and glacial retreat. In contrast, higher alpine zones remain largely untouched, allowing endemic species and specialized ecosystems to persist with minimal interference. Human activity is more of a local factor than a driver of ecological change at the scale of the range itself. The combination of uplift, erosion, and climate creates pockets of biodiversity at different elevations. Every ridge, slope, and valley offers unique conditions. Forests, meadows, rocky slopes, and ice fields are interconnected yet distinct. Species distribution follows this patchwork, with some plants and animals confined to tiny areas, while others have wider ranges. The continuous rise of the mountains expands the available habitats, offering new opportunities for life to adapt and thrive. Evolutionary pressures in the Himalayas are intense. Harsh winters, thin air, scarce food, and rugged terrain create strong selective forces. Species must survive extreme conditions or perish. Endemic plants grow low to the ground, resist frost, and reproduce in short growing seasons. Animals develop strong limbs for climbing, thick fur for insulation, and efficient metabolism to cope with limited oxygen. Every ecological zone imposes challenges, and species evolve in response, resulting in highly specialized forms adapted to narrow niches. The Himalayas' vertical range creates a form of natural laboratories. Scientists can study how life responds to altitude, temperature, and isolation. Comparisons between lowland forests, mid-mountain zones, and alpine tundra reveal how species adapt to gradients in climate, soil, and terrain. Uplift, erosion, glacial activity, and river carving combine to create conditions for evolution, driving the emergence of new species and the persistence of endemic populations. In this way, the Himalayas illustrate the deep connection between geology and life. The same tectonic forces that push peaks upward shape the habitats and ecological niches that support diverse species. The mountain's structure, slope, and soil, along with climate and glacial processes, determine where plants and animals can live. Life responds to the mountain's growth, creating a complex web of biodiversity that mirrors the physical landscape. From dense subtropical forest to barren alpine peaks, the Himalayas host ecosystems that depend on elevation, climate, and geological change. Endemic species thrive in isolated valleys. Glacial retreats provide new habitats, and uplift continually alters temperature and precipitation patterns. The ecological zones of the Himalayas are a living record of how life adapts to an ever-changing rising landscape, a direct reflection of the mountain's ongoing growth and geological dynamism. Humans have long lived near and around the Himalayas, observing the mountains, rivers, and forests, and learning to survive in the steep, rugged terrain. From the earliest settlements in the foothills, people have watched the movement of rivers, the retreat and advance of glaciers, and the occasional earthquakes that shake the land. Their lives depended on understanding the mountain's rhythms, noticing where landslides were likely, and predicting seasonal floods. This knowledge, passed down through generations, forms the foundation of indigenous understanding of the Himalayas' constant activity. Exploration of the mountains began in earnest centuries ago. Travelers, traders, and pilgrims crossed passes that connected valleys and kingdoms. They recorded observations about the terrain, rivers, and climate. Early maps were rough, yet they captured critical features: the positions of peaks, the paths of rivers, and the locations of glaciers. These journeys, often dangerous, provided the first detailed understanding of the Himalayas' scale and complexity. Travelers noted the variability of river flow, the presence of ice at high altitudes, and the signs of previous earthquakes, adding practical knowledge to local experience. Indigenous populations observed natural patterns carefully. Farmers and herders noticed subtle changes in slope stability, river paths, and soil movement. Villagers recorded which areas were prone to landslides during monsoons and which riverbanks rose or fell with flooding. They passed on stories about the mountains shifting, cracks opening, or rocks falling after tremors. Though not expressed in scientific language, these observations reflected a deep awareness of tectonic and climatic forces shaping the land. Communities adapted their homes, roads, and fields in response, showing a practical understanding of geological processes. Scientific study of the Himalayas began systematically in the 19th and 20th centuries. Expeditions organized by universities and governments sought to measure peaks, map valleys, and understand the mountain's geological history. Surveyors used triangulation to calculate elevations and distances, recording the positions of peaks, glaciers, and rivers. Early scientific observations confirmed what local knowledge had suggested. The mountains were not static. Peaks, ridges, and valleys were shaped over time by both tectonic forces and erosion, and earthquakes were frequent enough to leave visible marks on the landscape. Geologists established long-term research stations in key valleys and high-altitude areas. These stations measured rock movement, recorded glacial melt, and monitored river flow. Instruments such as seismographs captured tremors, and temperature and rainfall gauges collected climate data. Scientists returned to the same locations year after year, documenting subtle changes in elevation, slope stability, and ice coverage. These repeated observations revealed patterns that could not be seen in a single expedition, showing that the mountains are dynamic systems shaped by multiple interacting forces. Satellite technology revolutionized human understanding of the Himalayas. Satellites measure elevation, track glacier movement, and monitor river flow with precision. GPS systems installed across the range allow scientists to detect shifts in the land as small as a few millimeters each year. Remote sensing captures changes over wide areas, revealing patterns of erosion, uplift, and glacial retreat that are impossible to observe from the ground alone. These technologies provide a continuous view of the mountains, making it possible to study the Himalayas' growth in near real time. Observations from space confirm that the Himalayas are still rising. GPS measurements show that the Indian plate continues to push northward, causing the mountains to grow by several millimeters each year. Satellites capture how rivers adjust to changing slopes, how glaciers retreat or advance, and how landslides reshape valleys. These data, combined with ground observations, allow scientists to connect the movements of the Earth's crust to the visible landscape. They can predict areas of higher seismic risk, potential flood zones, and regions where erosion is accelerating. Human exploration also contributed to ecological knowledge. Researchers documented plant and animal distributions, linking them to elevation, slope, and exposure. Expeditions noted where forests ended, where alpine meadows began, and how glaciers shaped habitats. Indigenous knowledge combined with scientific study revealed the connections between geology, climate, and life. Mapping these ecological zones showed how uplift and erosion create niches for species, and how rivers and valleys facilitate movement and genetic exchange. Technological advances expanded the scope of observation. High-altitude weather stations provide data on temperature, wind, and precipitation. Drones capture images of inaccessible peaks and glaciers. Remote cameras record wildlife in difficult terrain. Seismic networks track earthquakes across hundreds of kilometers. Each tool adds detail to the understanding of the Himalayas' dynamics, revealing the ways in which uplift, erosion, climate, and human activity interact. Historical records of earthquakes are enriched by modern instruments. Long-term, seismic monitoring allows scientists to study fault behavior over decades. Observations of landslides, rockfalls, and river changes are combined with satellite imagery to create models of landscape evolution. The Himalayas' growth, once understood only through indirect observation, can now be quantified and visualized with high accuracy. Peaks, valleys, and glaciers are mapped, measured, and tracked in a continuous process. Scientific expeditions also focus on glacial dynamics. Ice cores provide information on past climate, snowfall, and erosion patterns. Observations of glacial retreat and advance inform understanding of how climate and tectonics interact. Sediment carried by meltwater reveals erosion rates and the movement of rock from peaks to valleys. These studies connect the mountain's physical growth to ongoing environmental changes, showing that the Himalayas' height, shape, and ecosystems are tightly linked. Local communities continue to contribute knowledge. Herders track snow cover, river flow, and slope stability. Farmers observe soil movement and rainfall patterns. Even mountaineers provide data on ice thickness, crevasse formation, and rockfall frequency. This citizen science complements formal research, enriching understanding of the mountains as a living, changing system. Indigenous observations of earthquakes, landslides, and river shifts often align with satellite and GPS measurements, reinforcing the continuity between traditional knowledge and modern science. Mapping has progressed from simple sketches to highly detailed digital models. Topographic maps record elevation, slope, and terrain features. Geological maps show rock type, fault lines, and folds. Vegetation maps chart forests, alpine meadows, and tundra. Combining these layers allows scientists to see how uplift, erosion, climate, and biodiversity interact across the entire range. The Himalayas are not only measured geographically, but understood as a system of processes, each influencing the other. Human observation also reveals the pace of change. Comparing photographs, maps, and satellite images over decades shows glaciers retreating, rivers shifting, and landslides altering valleys. Peaks rise slowly, but subtle changes accumulate over time. Monitoring these dynamics is crucial for understanding hazards and for studying how the mountain's growth affects ecosystems, water resources, and human settlements. Humans are both observers and participants in the ongoing story of the Himalayas. Long-term research in the Himalayas informs global science. Observations of uplift, erosion, glacial movement, and seismic activity contribute to understanding of plate tectonics, mountain building, and climate interactions. Lessons learned in the Himalayas apply to other ranges, revealing how tectonic forces and climate combine to shape the Earth's surface. In this way, human observation connects local knowledge with global science, turning the Himalayas into a living laboratory for understanding the planet. The continuous push for exploration has revealed surprises. Some valleys rise faster than expected, while glaciers respond unpredictably to climate change. Landslide-prone slopes shift without warning. Monitoring stations and satellites provide data that allow predictions and risk assessments, helping communities adapt. Technology allows humans to witness processes that take centuries or millennia, providing insights into forces otherwise imperceptible at a human timescale. In this way, human interaction with the Himalayas is both practical and scientific. Indigenous knowledge guided survival, exploration revealed the mountain's scale and structure, and modern instruments quantify ongoing changes. Observation connects generations, linking stories, measurements, and technology to understand the dynamic processes shaping the tallest mountains on Earth. Humans have become observers, recorders, and interpreters of the Himalayas' growth, translating movement, climate, and erosion into knowledge that guides both science and society. The Himalayas will continue to grow in the future. The Indian plate is still moving north, pushing against the Eurasian plate. Scientists can measure this movement with GPS and other instruments. The plates move at a few centimeters each year, but over decades and centuries, this small motion adds up. Peaks will rise slowly, valleys will deepen, and the overall shape of the range will change. This motion is predictable in broad terms, but small variations in the Earth's crust can cause unexpected shifts. Models of plate motion help scientists forecast future growth. Using data from earthquakes, uplift measurements, and GPS, they can estimate which regions will rise faster and which may move more slowly. The highest peaks, including Mount Everest and K2, are likely to increase in height by millimeters each year. Slopes that are already steep may become steeper, and valleys will adjust as rivers cut through rising rock. These models also show where strain is building along faults, indicating regions of higher earthquake potential. Seismic activity will remain a defining feature of the Himalayas. Earthquakes occur when stress from plate motion is suddenly released along faults. Scientists expect large earthquakes in some areas over the next century, while smaller tremors will continue throughout the range. Seismic events will shape valleys, shift slopes, and influence erosion patterns. Communities and infrastructure near active faults must be prepared for these events, as earthquakes can trigger landslides, rockfalls, and flooding, affecting both the physical landscape and human life. Rivers and valleys will respond to ongoing uplift and erosion. As peaks rise, rivers will adjust their courses, cutting deeper into rock and forming new terraces. Sediment carried downstream will continue to build floodplains in lower areas. Some riverbeds may shift dramatically during floods or landslides. Over centuries, new valleys may form. Old valleys may deepen, and the landscape will continuously evolve. The flow of water will always reflect the balance between uplift and erosion, guiding the long-term shaping of the mountains. Glaciers will also respond to both climate and tectonics. If temperatures continue to rise, many glaciers will retreat, exposing rock and creating moraine-filled valleys. Meltwater will feed rivers, affecting sediment transport and valley formation. In colder periods, glaciers may advance, carving new channels and reshaping landscapes. These cycles will continue to influence the Himalayas' form and contribute to the ongoing balance between growth and erosion. Long-term geological evolution can be projected over millions of years. The Himalayas will not remain static. Peaks will continue to rise, valleys will deepen, and rivers will carry sediment to plains far from the mountains. The combination of plate motion, uplift, erosion, and glacial carving will maintain the rugged terrain. Over geological time, new ridges, passes, and peaks will appear, and the range will continue to evolve as a record of Earth's tectonic activity. Climate will remain an important factor. Monsoon patterns and snowfall will continue to influence erosion and river flow. Areas receiving heavy rainfall will experience faster erosion, while drier zones will see slower change. Seasonal and long-term variations in temperature and precipitation will affect glacier size, river volume, and landslide frequency. The interaction of climate with tectonics ensures that the Himalayas remain dynamic, their landscapes constantly responding to environmental conditions. Human settlements will continue to be affected by mountain growth and seismic activity. Communities in valleys must adapt to rivers that shift, landslides that block paths, and earthquakes that alter slopes. Predictive models allow scientists and planners to anticipate areas at risk, helping reduce hazards to life and infrastructure. Monitoring rivers, slopes, and fault lines will remain essential for understanding how the mountain's growth influences human activity. The mountain's biodiversity will also adapt to ongoing changes. As elevation shifts and slopes adjust, ecological zones may move upward or downward. Plant and animal species will respond to changes in temperature, moisture, and habitat availability. Endemic species may face challenges if suitable habitats shrink, while others may colonize newly available areas. Uplift and erosion, combined with climate change, will continue to shape the distribution of life across the range. Even with precise models, some events are unpredictable. Large earthquakes, landslides, or glacial lake outburst floods can rapidly reshape parts of the landscape. These sudden changes complement the slow, steady rise of the mountains, demonstrating that long-term predictions must account for both gradual and abrupt processes. Over centuries, both slow and fast events combine to create the Himalayas' evolving terrain. The balance of growth and erosion will continue to determine the highest elevations. While peaks rise slowly due to tectonic forces, erosion by rivers, glaciers, and rainfall removes material. In some regions, erosion may slightly outpace uplift, while in others, the mountains continue to climb. Over long time scales, this interplay produces the dramatic peaks and deep valleys that define the Himalayas. Monitoring technology will play a key role in understanding future changes. GPS stations, satellites, and seismic networks will track plate motion, river shifts, and slope stability. This continuous observation allows scientists to refine models of uplift, erosion, and seismic risk. By combining technology with field studies and local knowledge, humans can anticipate changes, plan for hazards, and learn how the mountains will continue to grow over time. Future rivers and valleys will also reflect tectonic activity. As uplift raises sections of the range, rivers will incise deeper, creating gorges and terraces. Sediment transport will continue to shape plains far from the mountains. Seasonal flooding will adjust river courses, and landslides will redirect flow. The Himalayas will remain a constantly changing landscape where water, rock, and ice interact with tectonic forces to create new features. Seismic patterns will guide the mountain's long-term evolution. Strain accumulates along faults as plates push against each other. When released, it reshapes slopes, triggers landslides, and sometimes alters rivers. Over centuries, repeated earthquakes adjust valleys, slopes, and ridges. This ongoing seismic activity ensures that the Himalayas remain dynamic, not just rising slowly, but continuously rearranging their features through both gradual and sudden movements. Glacial retreat and advance will continue to influence the landscape. As glaciers melt, valleys are exposed, rivers swell, and sediment is redistributed. When glaciers advance, they carve new channels and deposit moraines, creating fresh habitats for plants and animals. Ice acts as both a sculptor and a force that affects crustal pressure, influencing the balance between erosion and uplift. The Himalayas' future form will reflect the ongoing interplay of ice, water, rock, and tectonic movement. In summary, the Himalayas' future is shaped by plate motion, seismic activity, erosion, glacial dynamics, and climate. Peaks will rise slowly, valleys will deepen, and rivers will adjust their courses. Glaciers will continue to advance and retreat, shaping valleys and transporting sediment. Ecosystems will shift in response to changing conditions, and human settlements will face ongoing hazards from earthquakes, landslides, and floods. These processes combine to create a dynamic, evolving landscape that will remain active for millions of years. The mountain's long-term evolution is a story of balance. Tectonic uplift drives peaks higher, while erosion and climate wear them down. Rivers and glaciers carve the terrain, moving material to lower elevations. Seismic events reshape slopes and valleys. The Himalayas are far from static. They are living mountains, their form continuously molded by the forces that created them and the processes that follow. Humanity can observe, study, and model these changes, but the mountains will continue to respond to the Earth's inner and surface forces long into the future. Even small changes in plate motion or climate can have long-term effects. A slight increase in uplift rate may allow peaks to rise faster. Variations in monsoon intensity can accelerate or slow erosion. Glacial retreat can expose new valleys or create temporary lakes. Each of these factors contributes to the ongoing shaping of the mountains. The Himalayas will continue to evolve, their dramatic landscapes recording the history of Earth's movement and providing insight into future geological processes. The Himalayas are part of a larger story of mountains on Earth. They are not the only tall ranges, but they are among the youngest and most active. When compared to the Andes in South America, the Rockies in North America, or the Alps in Europe, the Himalayas stand out for their rapid growth and high peaks. While other ranges were shaped millions of years ago and are slowly eroding, the Himalayas are still rising. The crust beneath them is thickening, rock layers are folding, and tectonic forces continue to push the land upward. Each mountain range tells a different geological story. The Andes rise along a subduction zone, where one plate slides beneath another. The Rockies form through earlier tectonic collisions and have slowed in growth. The Alps result from a collision of the African and Eurasian plates long ago, and today they are eroding more than they rise. The Himalayas, in contrast, remain a young range, a place where the forces of the Earth are still visibly reshaping the land. Their peaks reach greater heights than almost any other mountains, and the processes that create them are ongoing. Understanding the Himalayas in this global context highlights the dynamic nature of Earth's crust. The planet is not solid or still. It is composed of plates floating on the semi-fluid mantle below. These plates move, collide, and slide past each other, building mountains, opening seas, and forming valleys. The Himalayas are a vivid example of how collision between continental plates creates some of the tallest landscapes on the planet. The mountains themselves are records of this movement, showing layers of rock pushed upward, folded, and fractured over millions of years. The scale of the Himalayas reflects the energy stored in the Earth's interior. The northward push of the Indian plate releases immense forces at the collision, at zone. Rocks are crushed, folded, and lifted. Earthquakes occur as stress is released. Rivers carve valleys, glaciers reshape slopes, and erosion carries debris to distant plains. All these processes are part of the same cycle that links the crust, the mantle, and surface processes. The mountains are not static monuments. They are active, evolving landscapes shaped by energy moving deep within the Earth. From a broader perspective, the Himalayas show that mountains are living landscapes. They rise, fall, and change in response to tectonics, climate, and erosion. Peaks may grow taller, valleys may deepen, and glaciers may advance or retreat, all within observable human timescales. Life on these slopes adapts to these changes. creating a dynamic interaction between biology and geology. Species evolved to survive cold winters, steep cliffs, and shifting rivers. Rivers shape valleys that humans use for agriculture and settlements. Glaciers sculpt new landforms that will support life for centuries. The Himalayas also remind us of Earth's interconnected systems. The rise of these mountains influences monsoon patterns, river flow, and sediment transport far beyond their borders. Meltwater feeds major rivers that sustain millions of people in India, Nepal, Bhutan, and China. Erosion affects plains thousands of kilometers downstream. The mountains' growth and erosion link the inner Earth to the surface, the climate to rivers, and tectonic activity to human life. They are part of a living system that extends from deep within the planet to distant oceans and plains. In a philosophical sense, the Himalayas reflect the idea that landscapes are never truly still. Even the highest, most imposing peaks continue to shift and change. Time for the mountains is measured in millions of years, yet subtle changes are visible over decades. Glaciers retreat a few meters each year. Slopes shift, rocks tumble, rivers adjust, and faults creep. The mountains remind us that the Earth is alive in motion, that even solid rock participates in a slow but constant transformation. Standing before a Himalayan peak is to witness the result of deep time and immense forces. Each ridge, valley, and summit carries the story of plate collision, uplift, and erosion. The scale and pace of these changes dwarf human experience, yet they continue in ways we can measure, understand, and reflect upon. The Himalayas teach that landscapes are both powerful and fragile, enduring and impermanent, shaped by forces we can observe but never fully control. Viewed from space, the Himalayas are a thin white and brown ribbon across Asia, the product of processes that began tens of millions of years ago and continue today. From a cosmic perspective, they are small features on a planet orbiting a star, yet their growth and activity are vital to understanding how Earth works. They exemplify the principle that the surface of our planet is dynamic, that tectonic motion and climate interact constantly, and that the mountains themselves are a visible expression of energy moving beneath the crust. The Himalayas, like all mountains, are living records. They hold clues about Earth's past, show the present interaction of tectonic and climatic forces, and hint at the shape of the landscape in the future. Peaks rise and fall, glaciers advance and retreat. Rivers carry sediment to distant plains, and species evolve within newly formed habitats. Observing and studying them reveals the ongoing story of the planet, a story written in stone, ice, and flowing water. In this final view, the Himalayas can be seen as more than a geological feature. They are a reminder that the Earth is alive in motion, that landscapes evolve over time, and that the forces shaping our planet are powerful, continuous, and interconnected. They stand as a testament to plate tectonics, to erosion, to climate, and to life's ability to adapt to a changing world. The mountains are not fixed monuments. They are dynamic, breathing landscapes, rising steadily toward the sky, while continuing to respond to the forces that created them. The Himalayas, when placed in context with other great ranges, show how variation in plate motion, climate, and geological history produces different landscapes. While the Andes, Rockies, and Alps illustrate older, slower processes, the Himalayas are young, active, and growing. They offer a rare opportunity to witness the power of Earth's inner energy expressed on the surface, a natural laboratory for understanding how tectonics, erosion, and climate work together. Ultimately, the Himalayas are a reminder of the Earth's vitality. The mountains continue to rise. Rivers continue to carve valleys. Glaciers continue to shape slopes, and life continues to adapt. Observing them offers insight into geological processes, ecological dynamics, and the planet's long-term evolution. They are living mountains continuously molded by forces deep within the Earth and forces acting on the surface, a testament to the ongoing motion and resilience of the natural world.